For thousands of years, building a bridge meant hauling stone, cutting timber, and hoping it held. It was slow, dangerous, and brutally hard work. But something changed. The machines got bigger, the materials got stronger, and the methods got smarter. Today, engineers are dropping entire bridge sections from the sky, floating pre-built spans across oceans, and driving foundations deeper than a 40-story building into riverbeds. Modern bridges aren't just bigger than anything built before, they're built in ways our ancestors couldn't even imagine. So what exactly changed? Let's find out. Before a major bridge can be built, engineers must first prepare the site by constructing a temporary access structure. Workers drive steel sheet piles into the riverbed to create a cofferdam, pumping out the water to expose dry ground. Timber or steel platforms are then assembled across the water, strong enough to support the enormous weight of piling rigs and heavy machinery. This temporary bridge becomes the lifeline of the entire operation, allowing equipment to reach precise foundation locations safely. Soft riverbed sediment is often too weak and unstable to support the enormous loads of bridge foundations. Left untreated, it would compress and shift over time, causing piers to settle unevenly or collapse entirely. Bauer Spezial Tiefbau uses the single-column mixing (SCM) method to improve underwater soil. A powerful drilling rig mounted on a floating barge rotates a large mixing tool deep into the soft seabed, simultaneously injecting cement slurry that blends with the existing soil. This creates hundreds of solid, reinforced columns throughout the riverbed or sea floor. These interlocked columns transform dangerously weak sediment into a dense, load-bearing foundation capable of supporting the enormous weight of bridge piers above. For wider water channels where temporary bridges are impractical, engineers mount piling rigs onto floating barges, anchoring them precisely at each foundation location using GPS and heavy cables. Once the equipment is in position, the piling process begins. Large steel or concrete piles are driven deep into the riverbed using powerful hydraulic hammers, which deliver thousands of tons of force with each strike. With a massive 300 kilojoules of impact energy and a 20-ton ram, Stark HHP-20 drives steel and concrete piles straight into dense soil and rock. Up to 90 precise blows per minute, each strike carefully controlled for maximum efficiency. The goal is to reach solid bedrock or dense soil layers far below the surface, creating a stable foundation that can bear the enormous loads of the bridge above. After hammering the hollow steel casing into the ground, a drilling auger or grab bucket is used to excavate and remove all loose soil trapped inside, creating a clean, empty shaft. The reinforcement cage is then carefully lowered into the casing, positioned precisely at the correct depth. A single reinforcement cage for a large bridge pile can weigh several tons and stretch over 30 meters long, yet must be placed with millimeter accuracy. Finally, concrete is poured to fill the shaft completely. Dozens of piles form a cluster beneath each pier, collectively distributing the bridge's weight across a wide area of ground. Steel reinforcement cages, often called the pile skeleton, are fabricated on-site before installation. Workers cut and bend thick steel rebars to the required length, arranging them in a circular pattern to match the pile's diameter. These vertical bars are then bound together using smaller circular hoops called stirrups, welded or tied at regular intervals along the entire length. The finished cage is lifted by crane and lowered carefully into the drilled borehole before concrete is poured, giving the pile its strength and structural integrity. From the completed foundations, whether sitting above water or on the ground surface, concrete piers begin their rise. Workers use self-climbing hydraulic formwork systems that eliminate the need for traditional scaffolding entirely. Once a section of concrete is poured and cured, the formwork automatically jacks itself upward to the next level, ready for the next pour. This remarkable system allows piers to climb skyward steadily, level by level, until they reach the full height required to carry the bridge deck above. Now that the foundations are ready, here's something worth knowing. Not all bridges are built the same way. Large modern bridges come in three major types: the beam bridge, the simplest, deck sitting straight on piers; the cable-stayed bridge, where cables shoot directly from a tower down to the deck; and the king of them all, the suspension bridge, where the entire deck hangs from massive cables draped between two towering giants, making spans of over 1.25 miles possible. For cable-stayed bridges, this stage becomes truly spectacular. The giant pylons, sometimes stretching over 200 meters into the sky, are constructed using the same self-climbing hydraulic formwork, rising section by section with extraordinary precision. These towering structures must be perfectly vertical and engineered to withstand enormous tensile forces from the cables that will eventually fan outward to support the entire bridge deck. At this scale, building a pylon feels less like construction and more like assembling a skyscraper above water. Both cable-stayed and suspension bridges rise on two enormous towers, the pylons soaring hundreds of feet into the sky, anchoring the cables that hold the entire deck in place. But building at that height creates a brutal engineering problem. How do you install cables on top of a 1,043-foot tower standing in the middle of a strait? For the 1915 Sanakal Bridge, the world's longest suspension bridge, spanning an incredible 1.26 miles, Liebherr's answer was audacious. They mounted two massive 357 HCL tower cranes directly on top of the pylons themselves. These cranes had to survive extreme weather, powerful maritime winds, and seismic forces, so Liebherr engineered a specially reinforced earthquake-proof configuration, allowing these giants to lift and precisely position the enormous structural components needed to string the suspension cables between both towers. Cable-stayed bridges work differently. Instead of one continuous cable draped across towers, each individual stay cable runs in a straight line, directly from an anchor point on the tower down to a specific point on the deck. Each cable is made of multiple high-strength steel strands, either threaded strand by strand through a pre-installed protective sheath, or prefabricated off-site as a complete bundle and pulled into position in a single operation. Once anchored at both ends, powerful hydraulic jacks tension each cable to an exact calculated force, tuning every stay like a string on an instrument until the deck geometry is geometrically perfect. While the main cables are strung, the bridge's steel deck is fabricated in factory environments to ensure structural precision. Companies like ISC use high-capacity CNC plasma cutters and automated submerged arc welding (SAW) to fuse heavy steel plates with longitudinal stiffeners, or ribs. This factory setting allows for shop fit-up, where massive sections are pre-assembled using laser tracking to guarantee perfect alignment. Once welded, the sections undergo grip blasting and receive multi-layer anti-corrosion coatings. Once the steel beams are fabricated, the real logistical challenge begins. Massive transport trucks haul these enormous sections across highways, each beam carefully secured, some stretching over 60 meters long and weighing hundreds of tons. But when water stands between the transport truck and the job site, barges take over, gliding steel giants across rivers and coastal waters with precision. Every delivery is a carefully choreographed operation, because one delayed beam can halt an entire bridge program dead in its tracks. Each beam is set onto pre-built piers or abutments, dropped into position with pinpoint crane precision, millimeter-perfect alignment every time. Heavy bolts are tightened through steel connection plates, then welds are sealed under intense heat and pressure, locking the entire structure into one rigid, unshakable unit.
But some bridges demand something even bolder. At Japan's Yamato Takeda bypass, engineers assembled an entire multi-girder ramp bridge unit flat on the ground. Every beam, connection plate, and steel joint completed before a single piece left the earth. Then, a 750-ton Liebherr crawler crane lifted the whole assembled unit in one single, breathtaking lift, swinging a fully built bridge section through the air and lowering it onto its piers with surgical precision. Next, corrugated metal decking is laid across the top flanges of the secured beams, spanning beam to beam, creating a continuous ribbed steel surface. This metal sheeting acts as permanent formwork, eliminating the need for temporary wooden molds below. Once the decking is fastened down, steel rebars are placed on top of it in a carefully engineered grid pattern, held at a precise height above the metal deck using small plastic or steel spaces called chairs. This spacing ensures the rebars sit at exactly the right depth inside the finished slab. Every intersection of the rebar grid is then tied together with wire, locking the bars in place and preventing any shifting or displacement when heavy concrete is poured over them. This is where TieBot changes everything. Developed by Advanced Construction Robotics, this fully autonomous AI-powered robot rolls across the bridge deck, using computer vision to locate every rebar intersection. No pre-programming required. It ties each one automatically, completing over 1,100 ties per hour compared to just 150 by a human worker, dramatically cutting labor time, reducing crew fatigue, and keeping large bridge deck projects on schedule. But what if you didn't have to tie a single bar on site? BAMTech does exactly that, manufacturing entire rebar layouts off-site in automated facilities, pre-tied, precision-engineered, and rolled up like a carpet. Crews deliver them to the bridge deck, unroll them according to a placement plan, and the reinforcement grid is done. No tedious bar-by-bar fixing, no days lost, just an entire slab's worth of rebar, placed, positioned, and ready for concrete in a fraction of the time. Installation time slashed by up to 80%. With the rebar grid fully tied and inspected, concrete is poured over the entire surface, flowing down into the ribs of the corrugated deck, surrounding every rebar and filling the deck from edge to edge. As the concrete cures and hardens, it bonds chemically and mechanically with both the rebar and the metal decking beneath it, fusing everything into one solid, unified slab. This slab then works together with the steel beams below through shear connectors, steel studs welded to the top of the beams, transferring load between the concrete deck and the steel, creating a single powerful composite structure capable of carrying enormous weight for decades. Bridges are constantly moving, expanding in summer heat, contracting in winter cold, and flexing under the weight of thousands of vehicles every single day. Without expansion joints, all that stress would have nowhere to go, causing the bridge to crack, buckle, or even collapse. So engineers deliberately leave precise gaps between deck sections, then fit them with tough steel-framed neoprene strip seals that stretch and compress with every movement, like a mechanical joint in the human body. Silicone sealants fill smaller gaps, and hidden drainage channels whisk away any water before it can attack the structure beneath, keeping the bridge alive, flexible, and safe for decades. Those same bridges are constantly exposed to rain, road salts, and freeze-thaw cycles that exploit every crack and crevice. And if water finds its way in, it corrodes the steel reinforcement, fractures the concrete, and quietly dismantles the structure from within. That's why waterproofing follows immediately after the expansion joints are set. The concrete deck is shot blasted clean, primed, then sealed beneath a continuous waterproof membrane, either bitumen sheet or liquid polyurethane, laid seamlessly across the entire surface. A protection board shields the membrane before asphalt is laid on top, while piers and abutments receive epoxy coatings of their own. Final tests confirm the system is fully watertight, ensuring that everything the expansion joints preserve, the waterproofing protects.
Before the bridge can open to the public, engineers perform comprehensive load testing to verify its strength, stability, and safety under real-world conditions. Dozens of heavy trucks, each weighing several tons, are carefully positioned across different sections of the bridge to simulate maximum traffic loads. These controlled tests push the structure to its design limits, while engineers monitor its response using highly sensitive instruments. Sensors placed throughout the bridge measure deflection, vibration, strain, and stress distribution in real time. Engineers analyze this data to confirm that the bridge performs exactly as designed and meets strict safety standards. Only after successfully passing these rigorous tests is the bridge officially approved and open for public use, marking the completion of one of the most complex engineering processes ever undertaken. Cable bridges don't just need inspection at inauguration, they require ongoing monitoring throughout their lifespan. For that purpose, engineers have developed specialized cable inspection robots equipped with sensors and scanners, allowing them to assess each cable quickly and with precision. They can detect early signs of wear or stress that the human eye would almost certainly miss. This smart, systematic approach keeps the bridge strong, safe, and reliable, securing that vital connection for every traveler who crosses it. You can see these robots in action on the Taoyuan Bridge, which relies on 168 cables to bear the weight of the deck and hold it steady against wind, waves, and the relentless punishment of heavy traffic. Bridges don't just need to be looked over from above, they need to be inspected below the deck too. But how do you do that on a structure standing hundreds of feet above the surface? That's exactly where the AB Line series comes in. This bridge inspection machine features a 20-meter hydraulic articulated boom and a rugged work platform, giving inspectors reliable access to hard-to-reach areas both above and below the deck. The AB20/S moves with agility, rotates to follow complex bridge contours, and creates a stable, secure workspace for personnel and tools. When structural engineers determine that a bridge is beyond repair, demolition doesn't always mean tearing everything down. Often, only the damaged section needs to be rebuilt, and that's precisely where companies like Priestley Demolition Inc. take over. First, roads below are closed and heavy excavators move into position. Workers remove power lines and prepare the structure for safe demolition. Then, powerful hydraulic breakers begin smashing the concrete deck, breaking the road surface into manageable pieces. Next, crews expose and remove the steel girders, the load-bearing beams that support the ramp. After that, giant excavators attack the concrete piers, the vertical columns that carry the entire structure's weight. Machines work around the clock, lifting debris and loading trucks bound for recycling facilities. Slowly, section by section, the massive ramp disappears completely. Bridge construction is one of humanity's greatest engineering achievements, a relentless pursuit of strength, precision, and innovation that shapes the world we move through every day. If you learned something new today, let us know in the comments below. We read every single one. Your support and feedback are what keep this channel going. If you haven't already, hit that subscribe button and we'll see you in the next one.